Hi everyone, in this video we're going to talk about confidence intervals. So the central idea here, and this is something that comes up again and again in statistics, is that when we do a study, what we really find is information about some kind of sample. But what we actually want is information about a population. Now because it's typically not practical to actually survey an entire population, what we want to know is if I know something about the sample, some sort of statistic, how can we estimate the population parameter? That's really what we want. So as an example, an election is coming up. We survey 1,500 voters and find that 52% of them are supporting our chosen candidate. Does that mean that our candidate will win? So here we're looking at a sample, right? The size of our sample, it says, is 1,500 people. And what we know is the percentage or the proportion of the population that are voting for our candidate. So this would be a proportion of 0.52. Now in this chapter we'll be talking about estimating different types of parameters, means and standard deviations and proportions, but in this particular video we're going to be talking just about proportions. So the proportion of our sample is 0.52. The way we write this is a little p with a hat on it. We literally call this p hat. So our p hat is 0.52, but what we want to know is what proportion of the population will vote for our candidate. And that's something that we just don't have. Unless we actually talked to every single person in the population, we don't know. But what we can do is make predictions. So there's sort of two different types of predictions we could make. One is what's called a point estimate, and this is really just the best guess we have for what P would be. Now, if we do a survey and come up with 52%, then that is really our best guess. So P hat would be our point estimate for the population parameter. However, we would not be surprised if we were a little bit off. So if it turned out that only 51% voted for our candidate, that wouldn't be surprising at all. We would expect that the population proportion was close to 52%, but we don't know exactly. In fact, we could be really far off depending upon how good our sample was. The other type of estimate is what's called an interval estimate, or what this book calls a confidence interval. So this isn't a single value, it's a range of values that are attempting to estimate what the population value could be. We can never be 100% sure about what the population value is unless we actually looked at the entire population, but we can make an estimate using this interval technique. So built into a confidence interval is what's called a confidence level. And typically these are percentages that are around 90%, 90, 95, 99. Those are very common confidence level percentages. This confidence level is the probability that our interval estimate will actually contain the unknown population parameter. So if you took samples over and over again and found a new interval, a new interval, a new interval, right? We're making different predictions about what the population parameter is. If you have, for example, a 95% confidence level, that means that 95% of our intervals would contain the population parameter. You can think of this as just sort of how sure are we that the real value or the population value is in the interval that we're giving. Something that goes along with this is the alpha value. This is the Greek letter alpha. It looks kind of like a little fish. And this is the error. So if we have a 95% confidence level, that would be an alpha of 0.05. 99% confidence level, alpha of 0.01. These are always listed as decimals rather than percentages, and you'll see this in the book. So it goes hand in hand with our confidence level. So if we're trying to estimate that population parameter, or in this case the population proportion, we're looking for an interval that looks something like this. So we're going to say our population proportion, this is how many of all the voters are going to vote for our candidate lies somewhere in between a lower bound and an upper bound. And we get the lower bound and upper bound from our sample proportion, that was the 52% in this example, and then we either add or subtract this number E, and E is called the margin of error. So you may have seen in articles something like, we believe that that 32% of Americans plus or minus 3% believe something. That plus or minus 3% is the margin of error. That's saying, how wide is your interval? How much above or below do we expect the population parameter might be? So for proportions, we have this formula for the margin of error. And this is a z-score, z alpha over 2. This is called the critical value, and we'll look at how to determine this in just a second, times this quantity here. This is the square root of p hat, that was our sample proportion, times q hat. And just like we saw with binomial distributions, q hat is just sort of the complement, or 1 minus p hat. So we have p hat times q hat over n, right? Again, that n was the size of the sample, and then a square root. This really represents a standard deviation of our samples. So this is coming from a binomial distribution. So the idea here is that our critical number times this standard deviation is giving us how much of a range of error we should have. So when we compute this margin of error, one thing that we have to determine is our critical value. And this is a specific z-score that's associated with our confidence level. So I'm looking at an example here. If we have a 95% confidence level, that means that our alpha is 0.05. So really we're looking at z of 0.05 over 2, or we could say this as z of 0.025. So the picture you want to be thinking of with these critical values is that with a confidence level of 95%, we're looking at a normal distribution where the area in the center here is 0.95, right? 95% of the data lies in here, but then we have this critical region on the outsides. This region on the outsides represents values that we are excluding. If we had 100% of the data, then our interval or our error would always be infinite, because we can never be sure how far the data could go. So these areas that we're excluding is actually our error, our alpha value. So that means that the total of these two areas is 0.05. Since this is divided in half, that means that one of the areas would be 0.025, and of course the other is the same. So when we try and find what this z-score is, what we're really looking for is a z-score with area to the left of this whole 95% or 0.95 plus the little bit on the left here. So if we're trying to find this particular z-score, this is going to be area to the left, 0.975. If you look in the z-score table for this 0.975, you'll see that it's down here at about 1.96. But I also wanted to point out that on our z-score table, there's this little box at the bottom that has confidence levels with the corresponding critical value. So this is a nice little shortcut. So we were looking at 95% confidence. That's a critical value of course, 1.96. Now, this will only work if you have a confidence level of one of these three possibilities. So if I had a confidence level of 80%, for example, we'd need to figure it out based on area. But you can use this as a little shortcut. So here's our confidence level. There are some requirements in order to use this process, and I'm not going to go over them very thoroughly here. I want you guys to read the textbook and read about what we need to be true in order to use this for a population parameter. But basically, one thing we need is that the sample that we have is actually random. If you don't have a random sample, say you chose a really poor sample, then there's no reason to expect that it's going to predict what the population parameter is. So we have to have a random sample, and that sample has to have at least 5 what we call successes and failures. So in this case, we're talking about a proportion. We're looking at how many people vote for our candidate and how many people do not. In the sample, there has to be at least 5 of both of those. Otherwise, the distinction is just too small to make. So all of those requirements are in the book, but you want to check those. So coming back to our original survey, we had this value of n equals 1500. Our population, or our sample proportion was 0.52. So if we want to use 95% confidence intervals, again, we look up our critical value, which we were just looking at. This was 1.96 times the square root of p hat was 0.52 times, and then q hat, which is, remember, q hat is 1 minus the p hat, or 0.48 in this case, all divided by our n value. This comes out to 0.0253. I'm rounding to 4 decimal places here. One thing that I wanted to point out is with this formula, you'll notice that if your n value gets very large, then the error goes down. And this shouldn't be surprising. That means that if you have a very, very big sample, you have less error in your prediction, versus if you have a very small sample, the error will be a lot larger. So we take this error value, and we're going to take our p hat, which was 0.52, and add and subtract the error value to get the bounds of our interval. So 0.52 minus 0.0253 and 0.52 plus 0.0253. So we get an interval estimate of our population proportion that says somewhere between, this would be 49.5% and 54.5% of our population we predict will vote for our candidate. Another way that the interval estimate often is written is in interval notation, which is the first number or the lower bound, comma, the second number or the upper bound. So you may see that. Same thing. So if we wanted to know whether our candidate was going to win, say our candidate needs 50%, we can't be 100% certain here. It seems like the population proportion will probably be more than 50%, but our interval does dip down a little bit below 50. So we just found the confidence interval using a formula, but we can also use the calculator to do this. And in practice, this is the way I typically want you guys to do the confidence intervals. It's just a lot faster, and it's a little bit more realistic in terms of actual computations, but it's good to know both methods. So if you have your TI 83 or 84, we're going to go into the statistics menu, that stat button, and go over to the category tests, and we're going to pick the test that's called one proportion z interval. So one proportion means that we're looking at a proportion, of course. There's only one of them. We will look later at what happens when you have two proportions, and the z here is coming from the fact that we're using a z-score in the calculation. So it's going to ask us for certain information here. The C level, of course, is the confidence level. In this case, we were using 95%, so I can leave that as is. The N, of course, is the total number of the sample. This was 1,500 in our case. And X, just like with the binomial probabilities, X is the number of successes. So rather than giving it the p hat, which was 52%, we want to know, well, what was 52% of 1,500? So this would be 0.52 of 1,500. In this case, this is 780. So this would represent actually how many people in the survey said that they were going to vote for our candidate. All right, so we have 780 for X, we have 1,500 for N, our confidence level is 0.95, and then we hit calculate, and bingo, here is our interval. And this should be the same as what we had before. Sometimes it can be off a little bit because maybe the calculator is using a slightly different method of computing, but this is, of course, much faster than using the method by hand. Another thing you might notice here is if I go back through the same computation and put in a lower value of confidence, so say I changed from 95% to 85% confidence, you can think about, well, what would happen? If the confidence level goes down, it means we don't need to be quite as certain that the actual value will be in the interval. This is going to cause us to get a smaller interval. So you could think of this as a more targeted prediction. It's not as wide as the original, but we're less certain about what's going to be in there. Correspondingly, if I do the same thing but create a higher confidence level, maybe I do 0.99% or 99% confidence, the interval gets wider. And this should make sense because imagine you had to be very, very, very sure about your prediction. Well, you're going to predict a wider interval so that you have less chance of being wrong. So a very high level of confidence is going to create a wider interval. It's less targeted. And this is an important concept here. All right, so one more example here. We have a random sample of 450 high school students in the U.S., and 55 of these students attended private schools. And we want to know a 95% confidence interval for the proportion of U.S. high schoolers in private school. So what this problem is telling us is some information about what proportion of the sample was in private school. Our sample proportion, the p-hat, would be 55 out of 450. We could compute this as a decimal if we wanted. This is about 12%. What we really want is the percentage of all high schoolers in the U.S. and what percent of those go to private school. So we're going to make a prediction with our confidence interval. The x value here is the number of people who did go to private school in the sample, and is our total sample size, or 450. And we're going to use a confidence level of 0.95. In the homework problems, it should always tell you what confidence level you're using, but in practice, you would want to pick a confidence level that matches sort of how much error can you tolerate and how fine of a prediction do you want. So I'm going to do this with the calculator. Go into our stat and over to tests, down to option A. That was the 1 proportion z interval. So our x is 55, our n is 450, and we wanted a confidence level of 0.95. So here is our interval. We can write the interval in the interval notation just like this, or I could say that our population proportion, p, lies somewhere between 0.09196 and 0.15245. And we can say this with 95% confidence. So thinking of these again as decimals, this would be about 9.2% and about 15.2%. This is a much wider interval than what we are seeing with the voting example, and mostly that's because we have a much smaller sample size now. But we would predict that between about 9 and 15% of U.S. high schoolers are enrolled in private school based on this sample. Now, if we took a different sample, our prediction would probably come out a little bit different, but hopefully it wouldn't be too extremely different. Another thing I'd like to point out here, the sample size, right, this would be our n, makes a big difference in terms of your error on these calculations, but what actually doesn't matter is the size of the population. So even though U.S. high schoolers is a very large population, that doesn't actually make a difference. So the size of your sample is significant, but mathematically speaking, the population could be as big as we want, and it won't make a difference in terms of our prediction power. So here's a problem for you to try looking at confidence intervals. I did give you a confidence level that's a little bit odd here, so you'll have to compute your own critical number. And I will ask you to do this by hand first, and then you can check it with a calculator. So I'll ask for sort of the steps along the way. That's it for this video. See you next time.